Well, welcome everybody to the 9th in Contium series of meetups on the subject of artificial consciousness and related subjects. Today we're focusing on the subject of AI agents. Benjamin Rosman is a professor in the School of Computer Science and Applied Mathematics at the University of Witwatersrand in South Africa, where he runs the Robotics, Autonomous Intelligence and Learning Laboratory, RAIL. In 2024, he became the founding director of the Machine Intelligence and Neural Discovery, MIND. I'm very jealous of that acronym. That institute is at the University of Witwatersrand as well, and that's focused on the fundamental science of intelligence in machines, humans, and animals. And he's also a founder of Lilapa AI, building AI for Africans by Africans. Benji received his MSc in Artificial Intelligence and his PhD in Informatics at the University of Edinburgh. His research interests focus primarily on reinforcement learning and decision-making in autonomous systems, specifically on knowledge generalization and abstraction. He's a founder and organizer of the Deep Learning Indaba Machine Learning Summer School, which now has satellite events in 47 African countries. He's a National Geographic Explorer and a CIFAR Fellow at the Canadian Institute for Advanced Research. He's won a Google Faculty Research Award in Machine Learning and a Google Africa Research Award. And in 2020, he was made a senior member of the IEEE. But perhaps more excitingly than all of that, Benji was recently named as one of the world's top 100 most important and most influential people in AI all around the world. So hearty congratulations for that. As usual, we'll start with a presentation of 40 minutes or so from Benjamin. His title is Acting Rationally, the Challenge of Building Intelligent Agents. Then I'll abuse my privilege as chairman to ask some questions before we open up the conversation to the audience, and we'll close after 90 minutes. So please post lots of questions in the Q&A area, and remember, there are no silly questions. So Benjamin, thank you very much for joining us, and if you're ready, over to you.
Fantastic. Thanks so much, Callum. Yes, there's no silly questions, only silly presenters, as I will strive to be. So it's really great to be here. It's a huge honor, and we've been wanting to do this for ages. So I'm very excited that we finally had the chance. And let me just share my slides. Cool. So again, thanks for the invitation. Can you see the slides?
Yes. Yeah.
Great. Okay. Cool. So welcome, everyone. So I guess this is a series all on conscious AI, and I was thinking long and hard about what I want to present here. And I thought actually I'm going to kind of take a bit of a journey from the kinds of areas that I've spent a lot of my academic career and my research lab works on, which is really about building intelligent agents. Now, a couple of things that I want to flag here is that firstly, when I'm talking about agents, this isn't like the agentic AI of getting your large language model to go and, I don't know, buy and trade shares. This is kind of, I'll show you what we mean, but this is really more of the fundamental thinking of how we think about agents operating and working in different environments. And secondly, I want to point out that I'm going to focus mainly on intelligence rather than consciousness. Now, these, I believe, are very much orthogonal issues, but I think that there's a lot that we can learn from thinking about intelligent agents. Now, consciousness is obviously, and I'm sure has been discussed in every circle everywhere, a much harder thing to pin down, which I think makes it one of the very exciting topics of research. But as I'll talk about, I come at this from a very different angle, and I think there's some interesting takeaways that we can get from kind of approaching the question in this way. So what I want to do is talk a little bit about the areas that I'm interested in, that I've spent a lot of time working in, and see if there's some general principles and ideas that could be useful for kind of helping us build towards intelligent agents that might also have consciousness, which is something we're starting to look at in our research agenda. So with that said, let me dive into it. What I really care about kind of generally is robots, not necessarily just being the physical ones. They could exist in a virtual setting, but I care about these things and them doing all sorts of interesting, solving all sorts of interesting tasks, and particularly being able to work alongside people in a way that's meaningful, and ideally useful. And when I think about this setting, there's a few properties that would be ideal if our robots could exhibit them. Firstly, we'd like them to be flexible. And by that, I mean, I'd like my robots to be able to do a whole range of different things. I think it's fundamentally less interesting if all it can do is maybe weld one door onto one car in one particular location, or a little bit broader, maybe if it can vacuum my floor. What I really want is this kind of full diversity of being able to handle the rich, blooming, buzzing confusion of the real world. I'd also kind of like my robots to be instructable. And by that, I mean, I'd like to be able to give it different tasks. I don't want it to just say, all right, you're now, maybe a self-driving car, and you're going to just take me from A to B. I want to be able to describe in maybe quite a rich language the kinds of things I care about and what I would like it to do. And finally, when it does that, I would like it to be done reliably. So if I tell it a thing, or it's trying to carry out some task for some reason, I'd like it to actually execute the thing that I want, and do so with some sort of quantifiable certainty in the way that it works. Now, if we take these together, I kind of think of these first 2 points as talking about generalizability, and these second 2 points as talking about safety. So to me, this idea of building a safe general agent means it must be able to do a lot of stuff. It must be able to communicate with humans and take different instructions. And we should be able to predict in some way how it's going to respond to those instructions. So let me kind of make it tangible. And for a lot of this work, I'm going to use simulated worlds and environments just because that makes our life easier. But I'll talk a little bit about that more broadly as we go along. So this is the kind of setting that I might think about. Now, in general, I would like this to be a real robot in a real environment, but hey, those kind of experiments are difficult. So to keep things simple, let's say we've got this environment, which is, we've got a little robot guy over there, and he lives in this office world, and there's lots of things I might want it to do. So for example, I might give it a task that says, well, first I want you to go into the mail room. Okay, I don't know why we've got fancy robots and a mail room. This is some sort of weird hybrid future past scenario, but go into the mail room and collect the mail, and then deliver the mail to the people in this office that need their mail. And then maybe the people that didn't get mail are sad, so you should take the rest of them some coffee. Actually, just to check, can you see the words at the top there, or is it cut off by, I've got a bar on the top.
The words are there, that's fine.
Okay, perfect, fantastic. So take the rest of them some coffee. And maybe once you're done with that, you could patrol between locations 1, 2, 3, and 4 until someone needs something else of you. And while you're doing all of this, we've gone and spent a lot of money on these expensive decorations that we've got lying around the office, so I'd rather you don't bump into them and break them. So I might want my robot to do this. This is a pretty flexible task. There's a whole lot of things I want from it. Right? It's very intentional what I want. There's a whole lot of things that have to be achieved. And I would like it if this was done reliably. I don't want any humans run over. I don't want any decorations broken. I don't want the mail in the coffee and so on. So this might be the kind of task that I care about if I really want this kind of general agent that can operate in some environment. And I'm going to use this kind of scenario to really explain the way that we think about these kinds of problems. Now, to start at the beginning, you've got to learn to act in the world, right? You want your robots to be able to solve many tasks, and this requires learning. If those set of tasks are kind of open-ended, then it's going to have to be able to pick things up as it goes along. So how do we do this? Well, we're going to turn to an area of machine learning called reinforcement learning. And I'm going to just introduce a little bit of the modeling assumptions that come in this paradigm, and then talk about why they're not great for the kinds of tasks I care about. So it's a very general paradigm, and it models things this way. We've got our robot, which we'll talk about as the agent. And this is where we worked with agents long before the term agentic AI, where agent became an adjective, became a thing. But our agent exists in some environment. And what's important here is the interaction between the two. And this proceeds as follows. And of all the time, our agent gets to make decisions. And that's in the form of taking actions. Now, the action really describes anything that it does. This could be how it moves around the environment. This could be what it says, anything that it's got control over. So it's always taking actions in the environment. And in response, the state of the environment changes. Now, what does that mean? Well, if it moves 1 foot in front of the other, that state might have included the position of the agent. That's now changed. Or maybe the agent pushes a door open. The state of the door has now changed. This is an idea that whenever I take an action, it's got to have some sort of impact on the environment. Well, maybe some actions don't. That would be a useless action. But really, it's about this kind of this feedback cycle between these two entities. And then finally, it gets what we call a reward signal sometimes. Now, this reward signal tells it when it's done something that we like or don't like, right? So you could imagine if the agent falls down some stairs, we give it a negative reward. And the idea is that that's our way of saying to it, don't do that thing. Or maybe it brings us a nice cup of coffee, we give it a positive reward. That's our way of saying, that was excellent, do this thing a lot. And we can think of this as, to some extent, modeling the dopamine system in the brain of like, you get this like kicker when something good happens, you ate a delicious chocolate, and you get this kind of positive reward. When you ate the disgusting, whatever an anti-chocolate is, you get a negative reward. And your brain kind of uses this as a signal that you're trying to always gather as much as you can of. And so this very simple interaction then models, I can do stuff, the world changes as a result, and sometimes good, or like I've got a measurable idea of good and bad things. And we'll talk about all of these in turn. But just to point out, these actions and these states are typically quite low level. So for a robot, the actions might involve moving one of your joints by a few degrees. The state might be all the pixels I can see in the world in front of me, right? So these could be really high dimensional, really low level. I have to do a lot with them to make sense of them. And these rewards are also a bit challenging, and we'll talk about that a bit as well, like where do they even come from? But this is the standard paradigm for thinking about these decision-making contexts. Now, if you're doing reinforcement learning, we also need to start modeling this a little bit mathematically. And the way we think about that is through what's called an MDP, or a Markov decision process. And the standard MDP consists of 4 elements. And I'm giving the simple version here. There's more advanced ones that include partial observability and so on. But for our purposes for this talk, we can stick to the simple things. So what have we got there? First, there's the S, and the S refers to the states. As I said earlier, these in this very simple case might be, where is the robot standing? And it might be, is the door open or closed? Then we've got actions, and these might be things like go left, go right, open the door, grasp object. Like these are all the things the agent can do in this context. Then we've got this T, which we call the transition function or transition dynamics. And that says, if I'm in a state and I take an action, what happens next? So this like encodes the physics of the world. And finally, we've got these rewards. So this might be, if I fall into the hole, I get a reward of -3, or I get the present, I get a reward of 10. So this kind of mathematically encodes the entities that we care about in the environment. And if we know all of these things, we can solve the problem. So what does it mean to solve the problem? Well, actually, before that, again, just to recap, the states are typically very high dimensional. It might be, all the angles of my joints. This might be all the pixels I can see. This might be where everybody else is in the world around me. And the same of the actions, right? This could be all the motor positions of your joints. Okay, and then finally, the reward function tends to be task specific. So in this case, what we're saying is, if you're trying to get all the rewards, what we're saying is don't fall in the hole and get the present. Those are the things we want to achieve here. Now, what we really care about here are policies, and a policy is just a behavior. This is like a thing that your agent might do. So you could have a policy in this case that says, go right 4 times, then open the door, and then grasp an object. Okay, so it's just a sequence of actions, or more specifically, it's a function that tells you in any state of the world, what should I do there? Okay, any description of this is a policy, no matter how good or bad it is. What we care about is trying to find the optimal policy. And that's like the policy that gets us the most positive reward and avoids all the negative rewards. So in this case, the one that I drew here probably is the optimal policy, which is go all the way to the right, open the door, and get the object. That would have gotten us that reward of 10. Now, the way we do this, unlike the rest of machine learning, is we learn through trial and error. And I'll show this a little bit in a second. Your agent really has to learn, because typically it doesn't know how the physics work, and it doesn't know what's desirable. It can't exactly predict everything. And so it's going to try stuff and see what happens. this is very much how we learn as babies. It's getting limited feedback. As you saw in my example, in this case, it only got feedback when it gets the object or falls in the hole. So if it sits in the middle going left, right, left, right, left, right, it's not getting any feedback about is it doing something good or bad. And this makes it hard to learn in these cases. Now, this reward itself, let's talk about that a little bit. What is this? So it's just a number that the agent gets sometimes. And as I said, that's a bit like this dopamine signal that it gets. But this is the thing that it learns from. So this is encoding things that we want it to do or not do in the environment. So, typically would say if you're learning to play a game, you'd get a reward for winning the game. Or maybe you'd get a negative reward for losing the game. Right? So if I'm trying to get an agent to play chess or Go, what you'd maybe incentivize is like give you a reward of 100 for winning minus 100 for losing. Maybe for colliding with an object, you'd get a negative reward. Or we could penalize things like going at high speed or using a lot of energy. We could maybe reward solving subtasks along the way. So it's really about anything that we care about that we want to incentivize. But this is really difficult to set. So firstly, from the agent's perspective, it doesn't get a lot of the signal, right? If I'm getting it to play chess, I might only give it reward when it finishes the game, like that positive or negative. But if it plays and it gets positive 100 or positive 1 for winning, now it's unclear to it, did it do well the whole time? Was it doing badly and then suddenly recovered or vice versa? This is a really hard signal to learn from. And secondly, from our perspective, this is really hard to set and kind of arbitrary. Did I give it 100 for winning, or did I give it 723 for winning? Did I give it minus 12 for exceeding the speed limit? Like, it's all kind of arbitrary, but how I tweak this makes a huge difference and can lead to some very undesirable behavior if I set it wrong. Okay, so how do we solve these problems? Well, typically, if we're getting rewards all the time, maybe one thing to do would be just to say at any point in time, take the action that's going to give you the most reward. But as I've been saying, this is kind of sparse and delayed. You don't get the reward signal a lot. So that's a hard thing to learn from, right? So for example, if I had my robot here and I took one step to the left and it gets a little reward, one step to the right and it gets no reward, maybe it's better to go left. But actually, maybe the full problem looked something like this, that one step to the left gets you a little reward, or 5 steps to the right gets you a huge reward. So you've actually got to be able to think ahead and not just choose instantaneously based on what's going on. And this is kind of a fundamental difference to, again, the supervised learning models, which we even see in like large language models that are kind of predicting the next token each time. What we really need to do to act optimally is to be able to think ahead, is like planning ahead. So to do this, we introduced this notion of value. I'm not going to go into the details too much, but this is really encoding how good a state is if we're thinking about the long-term reward. So what this would kind of say is the value of where this robot is now is maybe lower than the value of being 1 step to the right, which is lower than being 2 steps to the right, which is lower than being 3 steps to the right. And this gives us a kind of signal that says, based on what I might do in the future, how good is it to be where I am now? And we typically encode this as a value function. I'm not going to talk too much about that. I just need to introduce the terminology to show you some things later on. So what is the value function though? Well, it might look like this. Let's say our agent exists in this grid and it's going to move around and it's going to get some feedback when it gets to that present. And so what the value needs to do, because I can't just make a decision based on where I am because I might not get any instantaneous feedback. So my agent might just wander around randomly and it's getting no feedback. It's got no idea of what's happening until it gets that present. And maybe then it gets a reward of 100. So the kind of notion of the value function is that, well, if it got 100 there, then the state next to that is maybe worth 99. And maybe the state next to that is worth 98 and the state next to that 97 and so on. So the idea is like, if I can kind of attribute how useful that state was to getting to my goal, I can like notionally in my head carry some sort of idea that this was kind of more desirable than being earlier along in the trajectory. That's kind of what we're trying to encode here. So these are very kind of standard notions in reinforcement learning. Now, when the agent exists in its environment, it doesn't actually know how the world works. It doesn't know where the rewards are. It doesn't know what the transition dynamics even look like. So typically what it has to do is learn from experience, which again is quite different to the standard way we do machine learning, where you don't just learn from a big data set, you're learning from actually interacting in the world. So, we might have our agent there, we might get it to pick an action, maybe it says go up, and we see what happens. It moved over there and maybe didn't get any reward. Now, this becomes some data that it can learn from. This goes into kind of updating its value function and telling it what happens if I do certain things in the environment. Or maybe it's here and it tries to go up, nothing happens, and it gets a negative reward for bumping into something. And this is kind of its trial and error process for learning about the world, which incidentally is very similar to the way that we learn, particularly kind of as children, right? You put your hand on the stove, you get a big negative reward, and you learn not to do that again. Right? But as it's learning this, right, it's storing all this information in its value function. And it's using that as it's learning to decide what to do. So it's kind of learning and acting at the same time. And this is a standard kind of setting in reinforcement learning, so that as it keeps acting in the environment, it gets better and better. So it starts off acting usually pretty randomly, bumping into walls a lot. And over time, it starts building up these models of what it's trying to do. Right? Learning then looks typically like this. So if we look along the x-axis at the bottom here, where it says trials, this is just as it interacts with the environment more and more. And you can see as it does, it gains more and more information, so it's able to get more and more rewards. So this is what an agent learning in an environment typically looks like. Now, what I've described to you is great, and this has been around for decades, and we're able to solve all sorts of interesting problems with this. But the challenge is that the world is large and complex, right? So typically I'm not just, storing the value at each point in a grid. I've got to deal with all the nonsense that comes with having high dimensional cameras and complex robot arms and that sort of thing. And this is where we start hitting into trouble. So there's a standard toolbox we use where we go from reinforcement learning to deep reinforcement learning by throwing in neural networks to approximate stuff. And that's all very nice and good. But I don't think it really gets at the core of the intelligence problem. So these are the kinds of challenges that we look at. So the first is that learning is just generally slow, right? And we see this, we go from being a child to an adult to kind of slowly learn how to make our way through the world. We talk about this as being inefficient or bad sample efficiency. Your reinforcement learning or RL agent has to mess around in the world for ages to learn anything useful. And even worse, if there's a whole lot of different things I want to do, I've got to learn each one independently. So that's kind of rubbish because that takes forever. So we need some way of transferring knowledge between the different tasks we care about. And I want to show you some of the ideas that we've been working on in this space. So one thing to think about is maybe we could learn, instead of just trying to learn to solve each task, maybe we can learn skills, right? This is a kind of abstraction of our behavioral knowledge. And we can also learn something about these skills, when to use them and how to use them. So for example, in a different kind of video game, I might learn a skill which is go down a ladder. But more than that, I need to learn something about when I can use this. So in this case, what we're able to learn, I'm not going into the details of this, you can read the papers if you care about those technical details. What you need to learn here is I can use the skill to go down a ladder whenever I find myself standing at the top of the ladder. And the effect of that is that I'm now at the bottom of the ladder and I've got some ground under me. And this then becomes kind of a useful chunk of knowledge that I can use later on. In fact, if I then find myself in a complex world, if I just find all of the places that look like the top of a ladder, I know what I can do there, and then maybe know what I should do there. And I can use this for planning. And so we've shown that in some fairly complicated environments, if you piece this all together, you can, having skills around jumping, around picking up keys, around using ladders and levers and locks, you can piece this together to solve problems that are actually pretty complicated by learning these little behavioral pieces with the kind of state representations that go with them in terms of preconditions and effects. And you can take this to some fairly complex domains, but what's important actually here is that these are what we call egocentric representations. I've learned something about myself, which is an action that I can execute. And the representation I'm looking at here is about what's going on around me in the world. So you can see on the left here, this isn't a full map of the world that's important. It's that little view around me that I'm standing on top of a ladder. And I'll come back to this a bit later, but this is really about what does it mean for that agent to be in the environment? And I would take this to be the kind of embodiment of the agent as being important. So we've then shown you can solve fairly complex crafting problems in Minecraft using this kind of representation. If you're learning about doors and levers and chests and all sorts of things, right, we can very simply solve problems that can't be solved using other techniques, because this is about kind of factorizing our behavioral knowledge. But if we can learn more than just what's going on around us, we can actually learn how we interact with the things around us, we can do even better. So for example, in this environment, which is called Sokoban, which involves pushing these boxes around, we've shown how you can actually learn very simple rules. Like if there's a box next to you and nothing next to the box on the other side, you can push the box. But if there's something on the other side of the box, you can't push the box. And if you can just learn a few simple rules of like the physics of the environment, which in this case, we show you can learn very trivially as decision trees, turns out this gives you everything you need to solve much more complicated problems. So again, this is around this idea that if you can figure out what you need to pay attention to, and you can kind of reason about it at different levels of abstraction, you can solve really complicated problems and actually learn everything you need to solve those problems from much simpler instances of the problems. Okay. That was one problem. The next problem is that it's also difficult to define tasks. So I've spoken about this a few times, right? We define our tasks by our reward functions, which are just these kind of arbitrary numbers we throw out. But this requires expert knowledge. This requires us knowing like, okay, falling down a hole is bad, so I'm going to penalize that. Or stepping on a human is bad, let's penalize that, right? So I've got to kind of think about all of these things, and I've got to kind of fine tune the reward values of saying, oh, wait, this one should be a little bit higher, that one should be a little bit lower. And all of this ends up with these kind of unintended side effects, or what we call reward hacking. And we see this in so many examples, but the simple kind of examples, colleague of mine had a robot vacuum cleaner and decided to hack it because it wasn't going very fast. So decides, okay, what I'm going to do is give it a reward for how fast it's going. So the faster it goes, the bigger reward it gets. But obviously I don't want it crashing into things. So if the sensors in the front of the robot detect any upcoming objects, and it bumps into them, I'm going to penalize it. So what did this learn to do? Well, turning the handle, doing the reinforcement learning, what the robot learned to do was go backwards as fast as it can, because there's no sensors on the back to detect collisions. So it gets all the reward for going fast, but none of the reward for bumping into things. So we get this kind of unintended side effects problem. So how do we deal with this? How do we solve this kind of problem over here? And one way might be, can we define the tasks in a way that's a little bit more intuitive to us? Now, if we're thinking about these kinds of problems, what do we really care about? Well, I think we want our task to be human understandable, because we've actually got to specify what we want our agent to do, maybe at a very, very high level of abstraction. So for example, we might want to do something like do X and Y simultaneously, or do something until another condition's met and then do Y, right? We want to be able to specify this quite naturally, but without doing relearning every single time I want to learn a new task, because that takes forever. And also, ideally, this should be verifiable in some way, that like it actually is going to execute what I've asked it to. So how do we do this? Here's an example. So again, here's another little world where we've got our little agent, and there's different objects around it. There's boxes and circles, and they're different colors. Now, let's say I went to a whole lot of trouble to learn one task, which says, so that Q there just says what we're looking at is the value function, and that's going to say that how good is it to get a blue object? That's a little blue squiggle over there. So what this surface on top of the space shows me is kind of the desirability of certain states. So you can see that it's, wait, can I get a laser pointer perhaps? Let's see if I can find a laser pointer. Hopefully you can see that. So the two blue objects corresponding to the two opposite corners, you can see that they've got higher value, and it kind of decreases as I get further away from them. So that might be the output of the learning procedure that says learn to get blue things. Again, that would take ages to get. Now I could learn another skill. I could say, okay, can I learn to get boxes? And again, I get something that looks like this. We've got the value function that's at its highest around these three boxes. It falls off away from that. And if my agent then just moves up this gradient, it gets towards the more desirable things. Okay, so now I've gone to a lot of trouble to learn two different tasks. But can I do something with this? Right? Could I reuse this knowledge in any useful way without it doing any further learning? Because to me, okay, I can get my agent to learn to solve these things. And again, reinforcement learning does it really well. But like, if I can't use that knowledge some other way, is this really general? And turns out basically in the standard reinforcement learning framework, you can't. Right? So the kind of things I might want to do is, what if I want to get a blue object or a box, but something that isn't a blue box? Like, could I do this? Turns out not with the standard techniques. So we've been spending some time over the last few years working on kind of variants of this framework that let us do this kind of thing. So let's say we've got this environment, and I keep mixing up the environment just to keep it interesting. Let's say we've got this office world over here, and we've got our robot moving around. So to keep it simple, let's say there's tasks in a few different places, which I'm just encoding in green here. And these might be the different tasks that I care about. Now, we've changed the definition of the way the problem works slightly. And again, I'm not going into the mathematical details. We've got lots of papers on this. But fundamentally, we're going to think of these as internal goals with augmented rewards. So instead of the rewards being defined all arbitrarily, what we're going to do is say, if it's trying to reach a particular goal and it gets there, it's going to get a standard reward. But if it gets to the wrong goal, it's going to get a standard negative reward, which turns out to be the worst thing that could happen. So if it's trying to do something and it ends up doing something else, this is very bad. But while it's going about the environment, it's going to learn something that's a little bit different to the value functions that are standard in reinforcement learning. It's going to learn something we call a world value function. But what this does is it tells it something about, as I'm working towards one task and I'm moving around the environment, what is this telling me about the other tasks? Am I getting closer or further from them? Am I getting positive feedback or negative feedback? It's a bit of an idea of like, given all the things I can achieve in the environment, what am I learning about them as I'm solving each task? As I'm going to make myself coffee, what am I learning about how the fridge works? Or what am I learning about the chairs and tables and so on in the environment? So that's what's happening at an intuitive level. But fundamentally, this then becomes a model of kind of all of the behaviors and all the things that I might care about in the world. So again, instead of this just being that one surface, I've now got this quite complex surface that tells me about all the things I care about. Now, why would I go to the trouble to learn this thing? Well, for some interesting mathematical reasons. Maybe I won't go into this in too much detail, but let's say you've got two tasks. Each has a different reward function, and each has a different world value function corresponding to that. Basically, I can think about composition in my tasks. So there's a nice way that I can define what it means to do A or B, or A and B, or not A. And because of the way we've defined this, that translates directly into the solutions. And I'll show you what this means now. Don't worry about the mathematics here. All that this is saying is that if I've got some nice structure over my problem definitions, then for free, I'm going to get some nice structure over my solutions. So what does this mean? Is that if I've got some optimal base tasks, which was I know how to achieve A and I know how to achieve B, then I can get these compositions that say give me the solution to A or B, or A and B, or not A. I get those for free with no extra learning, so zero shot, and the solution is going to be optimal as well. And what that means is I get this kind of super exponential explosion of my capabilities of my robot. So if I've got just 10 base skills, I can solve like 10 to the 308 tasks, which is usually not how these things work. Usually they're not in our favor. The explosion's usually counting against us. So let me show you what that actually means. If we're in that environment and I've learned how to get the blue things and I've learned how to get the boxes, then under this framework, if I say I want to get something that's blue or a box, then just by doing a max operator over this, I get the optimal solution. So wherever the agent is, it will go to the closest thing that's either blue or a box. Similarly, if I say I want something that's blue and a box, I can just do the min operator, and from wherever it is, it'll go find a blue box. Or I want something that's not a box. Similarly, I get the solution for that. And then I can do these crazy things like I want something that's blue or a box, but not a blue box. And what's cool is I'm reusing all the knowledge that I have, and I'm not learning in this case. I'm saying I can actually plan with what I've experienced in the world. I can sit there and figure out a solution without acting in the world that's going to be the correct solution, and then I can just execute it. Okay, so that's nice. What can we do with this? Well, first let me show you some animations of a little ant robot. Like, so we might learn this skill. In this case, it might be quite complicated to move its legs to do that, to go to the top. I might learn another skill to go to the left. And then again, for free, I can do these compositions that say, go to the top or the left, or go to the top and the left, or go to the top or the left, but not the top left. Okay, now what's nice is that this maps very neatly to language. So we've shown how we can then combine this with things like large language models to give it an instruction in English that might say, pick up the red ball. Then this gets mapped through some sort of encoder-decoder type architecture into our Boolean expression, which then gets mapped into our behaviors. And we can even show that we can learn these things jointly. We can learn the behaviors and the language jointly so that as we give it more and more tasks, it gets better at solving this problem. So we can end up with things like this. These aren't exactly optimal, but I can say to it in English, go to the green chair or go to the red sphere. And it's going to learn in some sort of complex, rich world how to do this by piecing together these bits of knowledge. That it's learned something about green objects, it's learned something about chairs and red and spheres, and it's piecing this all together, which means it's much faster to learn than to learn the series of different tasks separately, and it's nice and generalizable. So this might be a good time to just throw in a robot demo because there are a lot of efforts to make. So just showing the same kind of tasks here, we can give instructions to our robot, which might care about regions that are at the bottom or on the side. We could get it to learn these things through fairly complex control procedures. So it can learn to go to the left, it can learn to go to the right, to the bottom, and then I can start giving it instructions. I can say, go to the bottom left. And I don't have to have taught it specifically how to do this, but it will learn how to handle that. If I've also taught it about going to the door, I can then say, go to the bottom and the left, not using the door. And here there's a bit of safety that starts coming into it because I can say there's certain constraints in the environment and I want you to use that. Go to the bottom and not the left. So go to the bottom right and finally go to the bottom right without using the door. And in each case, it doesn't have to do any more of the complex learning, which, trust me, is a pain on a robot. It's just piecing together what it already knows about the world to solve this problem. Conveniently, this kind of thinking is also useful in a multi-agent setting. So if I've got this first setting where my red robot's learning to go to the bottom and my green one's learning to go anywhere, or the second problem where my red one's learning to go anywhere and my green one's learning to go to the top right, I can then piece them together. And not only will they learn how to go to where I want them to go, but they'll even learn how to coordinate around not colliding, which is really handy and a difficult problem at the best of times. So again, it's this kind of same compositional principle. And then just finally for the robot demos, again, just because there are a lot of effort to do, at the top, I've got a skill where my robot has to fill that bin at the bottom with red blocks, and a skill on the right where it's got to fill the bin with blue blocks, and then I can piece them together. So say not red, which means I want the red bin to be empty. Or I want either the red bin to be full or the blue bin to be full, but I don't want blocks in both of them. So in each of these cases, so whether it's multi-agent coordination, it's packing or unpacking things in a manipulation setting, or it's navigation, you can solve these problems by piecing these skills together. I'm not going to play the full video in the interest of time because I'm over time. I've got lots to talk about. Apologies, Callum. I'm going anyway.
No, you're not over time. Don't worry, Benji.
Okay, fantastic.
Yeah,
but I guarantee I will be. So feel free to stop me at any point. Okay, so let's go back to this problem that I set out at the beginning, right? So now I can do things simultaneously, but this was a bit more complicated. This involved doing things temporally as well. I want to collect mail and take it to everyone in the office and then take them coffee, right? So there's more structure to what's going on here. So we then asked, what would it take to be able to address these kinds of problems? Well, to do this, we've actually got to factor in what we call this temporal reasoning, or specifically temporal logics, right? And this allows us to handle these very long duration tasks where you're not getting much feedback along the way. So it works something like this. If we've got some environment, right, we need to learn all the same basic skills as we did before. But then we're going to have another piece. We're going to have a piece where we want to specify a task in what's called a linear temporal logic, or an LTL, which is going to say things like do something and then do something else, or do something until something is true. We've got a mechanism that translates this into kind of a state machine that looks like this. Again, I'm not going into details. We then create something called a skill machine, which takes this state machine of what should be achieved when, combines it with the skills, and gives us something that tells you what skills to execute when. So this is now kind of factorizing without it having to execute in the world and figure this out. This is kind of getting the agent to plan and reason through what needs to be solved in the problem. And this will finally give us a solution. So this looks something like this. So in this case, if we've learned about the different items in the environment, we can piece them together. We can say navigate to the button, the little orange thing, and then to a cylinder. And the robot can piece that together to solve the problem for us. Or we could say navigate to one of those buttons, and then to a cylinder, but never enter a hazard region. So here we have an element of safety. We can say the hazard region in this case would be the blue circle. We can say that there's a thing and we want you to never violate it, and we can prove that it would never violate it. And we can do even more complex tasks. We can say navigate to the hazard, to the blue, and then to a cylinder, and then to another cylinder, but avoid the hazard while you do that. So these become very complex tasks, which again, we can specify in kind of natural human language, and they translate directly into these kind of complicated behaviors. Okay, so that gives us this very rich setting, which finally we can use to solve this problem. So just to give you a demonstration of what this looks like, remember I wanted my robot to deliver mail from the mailroom to the recipients in the office, and then take the rest of them coffee until there's no more orders, and then do some patrolling and never bump into the delicate objects. Now, this is a task that this agent's never seen before, but it's able to plan through it by using these kind of logical specifications and piecing together this kind of lower level knowledge that it's acquired over time. Right. We've even gone further to look at things that it can do counting. So in this case, it's got to take however many blocks are in the green one. It's not entirely clear here, but then what it has to do is based on the number it took there, take the exact same number from the other bins, which involves it having to count as well, which turns out for other reasons is a complex task as well. So we've been able to extend this in all sorts of ways. It gives us a very rich language of the tasks our agents can complete. So basically what I've shown here is that if we do this kind of logical composition, if we can reason over the skills that our agents have, right, that gives us this kind of flexibility, instructability, and reliability, which gives us kind of general and safe agents that can do these kinds of difficult tasks. Now, as a final thought, I've taken you through this journey of solving these kinds of challenges, but what do I think out of this is useful for building towards conscious agents? And I think a lot of principles here are important for this reason. Okay, so if we want to take these kind of just intelligent agents and get them to move into the kind of conscious space, right? What does that actually entail? Well, I think some of these lessons are as follows. Firstly, embodiment is key, right? So what does that mean? That means the agent has to have a body, okay, maybe in the broader sense, but not necessarily a physical one. What do we mean here? It's got to be able to act, and it's got to be able to sense. So it needs to be able to observe some information from the environment and act on it. And those actions need to affect the environment in turn. But what's key to this, I think, is this kind of egocentric representation. The fact that your agent needs a sense of like itself. Now, I'm not saying how to embody this in a subjective sense, but if its representations are based on what's around it rather than a kind of bird's eye view, that gives us something that's generalizable. That gives us something that's adaptable to different situations, right? Which is very different from the way we thought about these problems before, but it seems really key to being able to adapt. It seems really key to be able to deal with complexities and changes in the environment. And then, in terms of reward specifications, the way you specify tasks is important. So what I hopefully showed you in this talk was going from this idea of specifying arbitrary rewards in an environment to kind of a notion of, have I achieved the thing I set out to achieve or not? Now, being able to do this, again, gave us the sense of generality that was less fragile. It wasn't down to me kind of hacking and tweaking and fine-tuning the rewards specifically for everything. It was about, there's a set of things I might be interested in my environment. And if I can do the thing that I was trying to do, then something good happens. And if I can't do the thing I was trying to do, then something bad happens. Like, I think this kind of intentionality is really important for being able to learn about how your knowledge of the world comes together, and more about your own capabilities, your affordances, your real experience with the world. Then I think these hierarchical representations are important. And I showed this kind of as we were going through, both in terms of your representations of how you're thinking about the world and in terms of your own behaviors. And I think it's important that we have hierarchies across both of these modalities. So that, for example, was instead of me always thinking about my joint angles and my XY coordinates, I have hierarchical representations of skills, like walk down the ladder, and I have hierarchical representations of what I'm seeing in the world, like am I at the top of the ladder? Am I standing on some ground? Am I at a lever? That kind of thing. If you can build up these representations, that gives you a more compact space to reason in, which again lets you transfer to different situations, and it lets you reason more broadly, deeper into the future than you can if you're not thinking about these abstractions. Then I think it's important to have world models. The world model here was this world value function. Why do we need that? Well, that firstly, it's a thing that tells us something about the world in terms of how the world works, its dynamics, and also what is desirable or undesirable in the world. Now, this is important for you to be able to plan. If you don't have a model of the world, all you can do is learn. And it's clear that to some extent, we're learning all the time. Our brain is adapting all the time, but that's not how we're solving problems all the time. We're able to formulate plans without having to relearn how to move our hands every single time we want to move it around, or relearn how to walk every time we want to move around the environment. And this is, again, only possible if you're able to do some level of planning. So I believe that this is a key kind of aspect for agents that are generally capable and are able to kind of reason about the world. And finally, it was a bit subtle in the way we presented it here, but I think attention is absolutely key. Now, here, this came through in a couple different ways, and this particularly was in some of the earlier work I presented around learning what features are important, which ties into this egocentric representation. If I can focus on what aspects of the environment are important, again, I can reason better, I can deal better computationally with this kind of rich complexity of the world, but also about subtasks. So as you would have seen towards the end there, when I had my agent walking around the environment, in this case, I specified all the subtasks for it. You don't actually need to do that. I haven't gone that much into that in this talk, but as long as it's focusing on what it needs to achieve at any point in time and can kind of filter out the other stuff, it's better able to focus on that task. And my perspective is that this is very likely or very possibly a reason why we evolved consciousness in the first place, as a way to kind of filter out our attention to focus on what's important. This is a thing that maybe is less important for a machine. Well, if you build it in a different way, maybe it doesn't need to do that. But if you've got compute and resource constraints, as human brains do, and as I think machines should have, I think this kind of attention type concept is key. It doesn't have to be attention the way we think of like as an attention mechanism in a transformer. It has to be something, that's one example, but it's got to be some mechanism that allows us to filter and prune the information that we're acting on at any point in time. So from this kind of exploration into building intelligent agents, I think these are 5 general principles that to me come out of this work that I think are really key for us to think about as we're moving towards agents that are not just more and more capable, but are more and more showing kind of conscious attributes. So with that, I think I'm going to wrap up here. So I had a number of students and collaborators that were involved in various parts of this project. That's a slightly dated snapshot of my lab, but thanks to all these people that have helped with all these various bits and pieces of work. And you can go and read a lot of the papers that I've been talking about at our lab website. So thanks so much. I hope I'm roughly on time, and I hope that was interesting.
Well, that was certainly interesting. Benji, thank you very much indeed. Very clear, very easy to understand, and really very interesting. I've got a bunch of questions. I'm surprised there aren't that many questions in the Q&A yet, and I am a bit concerned whether the technology is working. So please, participants, do post some questions. There are a couple, but also let me know on the chat or somewhere if you're not able to ask questions for some reason. Anyway, let's start off with a couple that I've got. We're accustomed these days to thinking that everything's an LLM. The agents you've got in these simulations are obviously not LLMs. I assume they're not. How would you describe them? What are they?
So these reinforcement learning agents they're basically an abstraction tool. So I've always thought of reinforcement learning as the core AI problem. This is the thing that we care about. This is the, how do I learn to act in some environment? So if we rewind all the way back to the beginning, it's really that blob that's operating in the environment. It's the thing that has some notion of the states it has, the actions it has, a model of how the dynamics of the world work and what's desirable in the world, and the policy. So you can think of this as kind of a set of functions that it's been given or it's had to learn that lets it operate in this case. Now, what I like about this is it's a very general problem description, and I didn't pitch this talk in this way, but I think modeling this problem as like an MDP, I think is actually too general. So a lot of what I've actually presented here, we've been imposing restrictions on this thing, because I think that the general setup is too general. And I think if you've got a problem that's too general, it's harder to learn. So, by imposing extra structure, it makes it easier. So that's exactly what's going on. So we've got the thing that its kind of modus operandi is it gets to interact with the world at some regular interval. It gets to choose an action. The world changes as a result, and it receives some feedback sometime. And what it's trying to do is receive all the good feedback it can. To me, that's actually a good model of kind of the decision-making mechanism that kind of animals and humans are executing, if we've trimmed out a lot of the bells and whistles. But those bells and whistles are really how we make it scalable and how we make it work. Interestingly, in some of our more recent work, we're finding a lot of interesting ways of combining LLMs into this work, and we can maybe chat about that in a bit as well.
Yeah, no, that's interesting. We'll come back to that. Clearly, these agents are very simple, wandering around Minecraft, are very simple simulations. And of course, what we want is robots that fold our laundry and go and fetch us a gin and tonic and perform all sorts of quite complicated tasks that we do at work. What's the leap like from what you're doing here to that? I mean, obviously, people are already creating robots which fold laundry. I think the last one I saw took about half an hour to fold a shirt. How hard, how hard is it to get from here to there? And what does it take? Does it take mostly data, or lots more compute, or different types of models, or different algorithms? What's the sort of the bottleneck?
Okay, so that's a great question. And, what I've shown you has mainly been in simulation, although a lot of these environments are actually high dimensional. Like, we just feed the thing its pixels. And in the robot cases, it's still going to operate with joints and so on. So we've been slowly making the transition to the more and more complex robotics tasks. And, there's various challenges. One, working with robots is difficult. You need a bunch of dedicated people that know what they're doing. Now, if what it's trying to do is, again, this is very much learning through trial and error, where your standard paradigms are like, you take all the text of the internet, feed it into your LLM like a gajillion times, leave that running on AWS, come back a month later and it's learned a bunch of stuff, right? But in this case, like, we actually have to have it interacting with the environment. So it needs to either have a physical robot in a physical environment or a really good simulator. Because again, the way, if you think about when a baby is like just a few months old, it's waving its arms and legs around. It doesn't have like a good interface to map from like to its like intentionality. So like, it's just operating in this very high dimensional space, like waving things around. And over time, you start learning these like better interfaces. So if we wanted to do that on a robot, this would involve it falling over a hell of a lot. This would be incurring a lot of negative reward, but the negative reward might translate into my research grant budget. If it falls down too many times, and I've got to get this thing repaired, and it's got limited battery life and so on. So there's a lot of work that we and many others are doing now about starting to learn some of these behaviors in good simulators, and then find clever ways of transferring from the simulated environments to a physical robot. So it's not learning from scratch where like it doesn't even know how its joints work. It's doing that in simulation, transferring over. So now it's kind of got a shaky grasp of reality, and it's got to go from there. This is still very slow to learn. And I think because a lot of the frameworks aren't quite right, we're very confident about what we're doing now. So we've got some frameworks that we're starting to port from this kind of setting I've shown you to more real robots. But like, honestly, there's a lot of engineering challenges that go with that. To take it from what I think we've kind of nailed a lot of the mathematics and the algorithms here, but kind of scaling them involves more efficient learning, more efficient transfer from simulators to the real world, like having a bunch of people who can sit there and fix the hardware when it breaks and that kind of thing.
Yeah, it's expensive and very time consuming to deal with the messy real world. It does seem like robotics, both simulated and real world, is very unevenly distributed. So you're working to improve the basic principles here with very simple simulations. At another extreme, you've got Waymo, which has got a few thousand self-driving cars wandering around in, I think it's half a dozen American cities now, doing something which we don't let humans do until they're adults. So it's really complicated. And when you see these things driving, they're very impressive. You know, they can maneuver around a wing mirror in a very elegant way. And that seems like, oh, well, we're already there then. We've already got robots that can do incredibly sophisticated things, and yet we haven't. And again, we've got robots which can solve Rubik's Cube in seconds and actually physically do the Rubik's Cube thing. How do you explain this, that you've got, you know, what looks like extremely advanced robotics in some areas, but in other ways we're still stuck on the basics?
Okay, so that to me is the interesting challenge. Now, there's a couple ways people think about this. One, we handle a problem like the self-driving car with a hell of a lot of engineering. So someone's gone and spent a lot of time like building very specific pipelines and doing a lot of pre-processing and cleaning up the data and that kind of thing. And injecting a lot of human knowledge, right? A lot of ideas of like traffic lights are important, rules of the road are important. If you see a person, like here's some cautionary things you should do. So there's a lot of like these kind of structural biases built into it. Or you can take another approach, which is to use kind of out of the box reinforcement learning, which is incredibly powerful. So, you know, a lot of the Rubik's Cube solving things would be doing that. But the challenge is, as I've shown here, like you've got to kind of get it to relearn for every task, or you've got to re-engineer it for every task. So the big question that motivates us in our work, which we've got a whole other streams dedicated to other aspects of this, but if I've got a robot, then let's say I've got a humanoid robot that walks over to a Rubik's Cube and picks it up and solves the cube, right? I know how to solve the cube. We can build systems that do that. But now I want the same robot to walk over and get into a car and drive the car. Again, as you said, we can build systems that can drive cars very well. What we can't do is build the same robot that can do both of them. And to me, that's about having these generalizable representations, having it be able to attend to what's important for the different tasks that it's engaged in, be able to transfer knowledge, like behavioral knowledge. You know, the way it moves its arm to pick up the Rubik's Cube is actually similar to the way it moves its arm to hold the steering wheel or, you know, pull up the handbrake or something like that. So this is really what we're pushing towards here, is trying to have these more unified frameworks that allow it to kind of absorb this knowledge from different places, be able to figure out what is relevant for the subtasks that I'm working on, and be able to employ the relevant pieces of information as and when I need it.
Cool. Okay. Before I go on to some audience questions, I've got one more that I want to ask. I may have misheard you, but I thought I heard you say at one point that you can prove that your robots would never violate a principle that they're given. How do you do that? That's proving a negative, isn't it?
So it's based on a few things. Basically, this is under that compositional framework. If we know, like, certain requirements have to be met. So particularly, like the strong case for this is if all of my underlying behaviors are optimal, So that would be if my behavior for fetching coffee would be optimal and my behavior for delivering coffee is optimal and so on. Then kind of mathematically under that compositional framework, any composition where kind of the underlying distributions of everything stay the same, we can prove that the solution to that task will be optimal. Now, obviously, there are challenges, like if the world changes, right? So if it's like never seen a door before and suddenly there's a door, that's going to stump it. But like in these base cases, we've got proofs that these conditions will hold, and that just comes out of the mathematics of how we've built these systems, because they've been designed with this in mind. So then we've got like, we've looked at different kinds of softer versions that says if the world doesn't change by more than like essentially some percentage, then we can guarantee that it's going to be, we can put like probabilistic bounds on the performance. And I think this way of thinking to me is very key for thinking about safety in artificial systems. And again, it doesn't come out of just, building a system that doesn't have safety in it and then band-aiding on top of this. This is about really building the system from the core that has these kind of constraints or attributes in mind.
Okay, so the environment's got to be quite heavily constrained. So you haven't stumbled upon a way to ensure that superintelligence doesn't wipe us out. We can't start Skynet quite like this.
As long as it's not out of distribution. So as long as the environment. So if these separate pieces that you've learned are all kind of well represented in the tasks that you're doing, and it's not like varying wildly outside of the things you've seen before, then we can guarantee safety. And as it does vary from that, we can probabilistically guarantee it.
Okay. All right, some audience questions then. So large language models are starting to get better at the sort of things that you were showing. What are their current limitations, and how would a large language model approach compare from an energy perspective? But also, can you get them to do the sort of things that you are showing here?
So I mean, this is a great big open question. So, the big thing with large language models is that they're next token predictors, right? And I mean, this is something that's spoken about a lot. What it's trying to do is predict the next word in general, or the next token, could be the next action, but it's not doing that in terms of like, what these reinforcement learning systems do is they choose the next action based on a kind of full, almost simulated idea of what the future will look like. They can, in many cases, reason about counterfactuals and so on. A large language model is saying, given the context I've seen before, can I predict the next token? So it can do a certain amount of planning by doing this kind of chain of thought reasoning. So it can reason through stuff that gives it more context and so on. But it's got to generate a lot of kind of babble to do that. We know that's expensive. Training the large language model is crazily expensive. Similarly, training these reinforcement learning models are expensive, but they're expensive in different ways. They're not as data expensive, but they're expensive in terms of like actual time interacting with the world. And the inference in reinforcement learning is considerably faster and cheaper. So it is possible in some ways. So there's quite a lot of work where people have tried to set up large language models to do this kind of planning. They can do certain kinds of it. There are always bottlenecks again, because they're not designed for like thinking ahead. They're designed for next token prediction. My a kind of hypothesis we're working on at the moment is looking at the fusion of these two things. So, you could try and tweak large language models to do this kind of thing. I think it's not the right way to go. I think it's a very inefficient way computationally to do it from a data perspective. And part of the problem is, your data that you would need kind of grows exponentially with the kind of future horizons you would look into. If I want to plan one step ahead, I've got to think of like all the things I could do now. If I want to plan 2 steps ahead, I've got to think about all the things I could do now, and then all the things that could happen after that. And this gets exponentially worse over time. So on the other hand, large language models are like really good repositories of kind of some sort of common sense knowledge about the world. So we're doing a lot of work, and many other labs are as well, on looking at ways to fuse these different modalities. So I showed a simple one using large language models to translate between like natural language and more symbolic reasoning. But there's a lot of other things you could do. So for example, we've got other projects where we're saying, let's imagine you've got a robot and you want to pick up a mug. Now you could use a large language model to say, where should I pick up the mug? Well, maybe that depends on what I'm trying to do with it. So if I could give it, so from my reinforcement learning agent, if I could call my large language model and say, I'm trying to pick up a mug from this image, so probably a vision language model, and I need to pick up the mug to put it in the dishwasher, or I need to pick up the mug to drink from it. Where should I grab it? And maybe this could say from the handle, or maybe it could even annotate where on the image it should be. Now I need to do some sort of joint learning and like treat this as an input to my RL agent that says, okay, if I know what a handle is, then I know where to grab it. Or maybe I need to learn these two things jointly. So I think there's a lot of like rich and interesting ways to fuse these different modalities. We're exploring a lot of that because it's, you know, if someone magically gives your robot like all the knowledge of humans, but it lives in like the world of text or speech or something, like that's got to be useful for acting in the world, which is fundamentally the problem we care about.
Yeah, yeah. I mean, what we really want to do is combine embodied robots, which understand how to navigate around the world and do the things that you were showing in those videos. But so combine that with models that have got a model, combine it with agents, which have got a model of language, which is what LLMs obviously have. It's very hard to think about LLMs and what they are, what they do. The idea that they're predictive text machines is clearly true, but it doesn't capture what they do. When you ask one of them to give you a description of what a company does or a philosophical concept, it's not just putting the next obvious word. It's dealing with a concept, which is quite a complicated, multifaceted thing. So it's but of course they're black boxes. We still don't know what's going on inside.
Although that you know there's a couple of interesting things there, and like I think particularly what that means is it's got kind of an interesting latent space. Like it's seen enough about text, for example, that it's like abstracted from text space to concept space, which is super interesting. And again, I think like, you know, some part of me like I'm less interested in the text per se. I'm more interested in the knowledge contained within that text. So I think that's really interesting. So we try and look at projects like, can you take things like what is the latent space or this kind of concept space learned by a robot? What is the concept space learned by an LLM? And can we find interesting ways of mapping between them so that you get again the benefits of both?
Yeah, I like that. They've abstracted from the text space to the content space. So we've got a question from somebody who I think is actually Doug Leonard in disguise, although he has sadly passed. But anyway, so Anonymous has asked, I've got two children and they seem to learn basic rules like the gravitational effect when something gets dropped and occlusion. So the ball hasn't disappeared just because it rolls under a table. It's just not visible. And he's wondering if there's a set of base rules that allow you to generalize a robot's ability to interact with the world very effectively in the way that an animal can. Do you think there's a base set? And if so, how many rules and how hard would it be to implement them? Now, I think that's what Doug Leonard was trying to do with Psych. And he thought that once he'd given Psych 1 million instructions, that would be enough. By the time he died, he'd got to 25 million and it was nowhere near enough. And I think the general consensus is that you can't do it that way because it's not generalizable. But have I got that wrong?
I mean, I think this is a hard thing to think about. Like, I could imagine that there's, you know, like a finite set of primitive things that I need to know about the world, and like everything else is some combination of them. But I don't even know how I would go about like annotating that. I think, or like even if I could describe that. I mean, to some extent that must be true because, you know, there's like, I don't know, for at least the way we operate in the world, we're always like piecing together things we know in certain ways. And I think like I don't know how you could exhaustively think about it, but I think like what needs to be the case is you need to kind of riffing off what we've been talking about, you need to have some way of saying, like, through my interactions with the world, I start learning some. Now, it might be a set of discrete principles. I feel more that there's some sort of abstract concept space that I'm learning something about. And by kind of moving around in that concept space, I'm able to interact with different kinds of scenarios or converse around different kinds of concepts. And maybe the more I've encountered, the more I've learned, the kind of richer that space is, or maybe the more precise that space is. I think to me, very much kind of that almost distillation process is what learning and intelligence is all about. It's about saying, like, given the chaos of the world, I can take whatever I've like, if I'm a machine, right, I'm looking at like millions of pixels right now, but I can distill this down to, I'm staring at a computer screen and talking to Callum. And I can, like, maybe some of these concepts are a little bit nebulous. I've got ways of approximating them, but like, to be able to operationalize my sensory experience, it's got to be something that I can kind of contain in working memory, right? I've got to be able to say, like, there's like a bunch of principles like at play at the moment. Maybe I don't, maybe I'm not even conscious of them to the level that I could spell out exactly what they are. For example, trying to catch a ball that someone's head up into the air. Maybe I'm not like conscious of how gravity is operating in that exact moment, but like I'm kind of running some sort of predictive model on the trajectory of the ball so I can position myself. I've got some idea of the force it might come down with, so I know to use 2 hands to catch it, or one. So I've got this set of principles that I'm kind of slicing together in some sort of way. I think LLMs do a very similar thing, but again, their domain is very much the language domain.
Yeah, yeah. So what we need is, to complement large language models, we need large world models, which of course is what people like Fei-Fei Li and to some degree Jan LeCun are working on. Now, my colleague Tom Elish is very clever, and I don't really understand this question he's asked. I'm going to give it to you verbally. You might want to, I don't know if you can read it on the Q&A. I don't know if you can see it. Because I think it's a bit of a hospital pass to ask you to answer this with it expressed verbally. But here we go. Tom says, what's your experience with employing a hierarchical guided reward structure, starting with very constrained reward states and changing what is rewarded as milestones are reached, with some learning stages probably more suited for simulations, allowing a back and forth? I can imagine it being too synthetic a framework for what you're trying to do if you map out the learning landscape top down.
Okay, so I think I'm going to interpret this correctly, and if not, Tom, please correct me. So this ties into something that's like, this kind of guided learning is super useful. We've done quite a bit of work on this. The way I think about it is through a kind of paradigm called curriculum learning. And there's a lot that goes into this, but this is the idea that, like, and there's a whole lot of different ways to think about it. There's notions of curriculum learning, there's notions of reward shaping, and then the idea might be, I could give a couple different framings of this. So the one would be like, I don't know, I've got my agent that I want to learn to operate in office world or something. And so first I maybe take it and let it move around a simple room with no obstacles in it. And like, I reward it for getting from point A to point B, or something very simple. And like, this gives it the scaffolding to learn about motion. And now maybe or motion in a straight line. Then maybe I put a little obstacle in the middle of it and get it to go from A to B. And now it's going to learn about circumnavigating things. And, I can slowly make the environment more and more complex. And each time it's kind of bootstrapping off its previous one, with the idea being that to go through this sequence of learning stages is actually faster than like dropping the thing with zero knowledge into like the super rich, complex world and letting it learn from there. So it turns out this is a super useful principle to do. We use this a lot in our own work, in a lot of like some of these challenging environments we've been doing, like that's how we let them learn. In fact, we're trying to look at that as a way to go from simulation to real robots as well, that you can think of like some of these simple steps as being, in a very simple simulator, and then in a kind of slightly more realistic simulator, and then in a very realistic simulator. And each time you're kind of bootstrapping to these more and more complex settings before you drop it into the real world. And again, these principles seem to really speed up learning if done in the right way. And there's also bodies of work around trying to figure out automatically what is the next task that the robot can generate the task for itself based on where it thinks its limitations are, which I also think is really exciting. There's another angle to this, which I think is very cool as well, called reward shaping. There was a project I worked on with a student a few years back. We did something called Bayesian or belief reward shaping, where the idea kind of works like this. Like, let's say you want to get your agent to learn to play a game of chess. Okay. What you want it to learn to do is win the game. So the standard thing would be give it like some big reward for winning, like let's just say 100 points for winning and minus 100 points for losing. So now it's going to play like gazillions of games, and eventually it's trying to learn to maximize reward. But this is super hard because it's got to take a whole sequence of actions before it gets any feedback. And again, it loses the game. It doesn't know, was I playing really well and just messed up at the last minute, or did I play badly the whole way? It's got to go through this whole challenge of like attribution to, over the course of my life, did I do something silly? Now that's really difficult to learn from. So what you might do is give it more signal. What you might do is say, okay, but also you're going to get some points for every piece that you take on the board. Now, and maybe lose points every time you lose a piece on the board. Now, this is super useful because now instead of, you can think about the time to go from start to like ending the game might be 40 moves or 50 moves before you get any feedback. But the time to go from start of the game to, or from any point to like taking or losing a piece might be like, 5 moves or something or less, right? So it's getting feedback far more often. So that's great. It's like much easier to learn there. The problem is now if it's trying to learn to optimize rewards, then what it's going to try and do is try and win the game by taking as many pieces as possible and losing as few pieces as possible, right? Which is not the optimal way to play chess. Like in its mind, what it wants to do is completely destroy the opponent by taking every single piece, but not losing a single piece, right? Now, that's not actually what I wanted it to do. So the way we think about this is like that extra like reward you gave it, instead of thinking of it as the same as the reward for winning the game, we think of it as a bit of a like guidance signal. And so in the framework we built, but there's many ways to think about this, what we did was we kind of decayed it over time as it got better at the task. So we said, okay, at the beginning, as your kind of training wheels, I'm going to give you some points for every time you take a piece, and you're going to lose points every time you lose a piece. But over time, those points are going to become less and less, like a smaller and smaller signal. And that's kind of similar to the way we might teach kids to play chess, which would be, okay, you've got to try take the other guy's pieces. Okay, so you're good at that. Okay, and then as you learn a little bit about how the game works and you get a little bit more competent, you can start saying, actually, that's not so important. What's important is you got to get the king. And, so there's different ways that you can, we've got to think about the way we're giving knowledge to these agents. Now, one way that this can happen more automatically, and I realize I've been rambling on quite a lot now about this, but I think it's really exciting, is kind of ties to a whole lot of things that come in through surprise minimization or driven by curiosity. There's ideas from the free energy principle. Like a lot of frameworks try and get at this, where the agent can like get some reward for doing something new or discovering something. But once it's learned about it, the kind of dopamine hit starts leveling off. And I think this is a kind of important principle, that what we're trying to optimize for changes over time based on, and that's intrinsically tied to our knowledge. And so that kind of drives us in the self-curiosity type cycle that we incentivize ourselves to discover new things. And that acts as a kind of extra layer on our reward, in addition to like, don't burn your hand or fall down the staircase. So I hope that was kind of what you were getting at with the question.
Yeah, actually, I think that was such a good answer. It helped me to understand what Tom's question was about. Tom is still here, I think. So if he doesn't think his question was fully answered, I'm sure he can follow up. I like the idea of giving the models a dopamine hit whenever they come up with something innovative. I wonder what sort of dopamine hit that AlphaGo should have got when it came up with move 37 in game 2.
Actually, there's an interesting comment on this, because like the whole line of work around Go playing came from David Silver, who's a big name in reinforcement learning, and there was an interesting observation that when we play a game like Go, what you're trying to do is like win the game, okay? But now the way that a human thinks about it is like, it's very hard to judge if you're going to win the game or not. As one of those properties of Go, that it's really hard to figure out like exactly who's up at any point in time. So that we need like a proxy for, like,
What's a good position to be in?
like exactly, right? So typically it seems like the kind of natural human proxy is to say, like, how many points am I up by? Is the proxy we use for saying like how good a position is this, right? Which is okay, but something we kind of discovered through AlphaGo is that's not the right proxy, because the proxy that AlphaGo uses is, what is my probability of winning? Which is actually what we want to have as a human. We're just bad at judging that. So it turns out that, like, from the way that this was built, essentially what it was doing, it's like a value function estimation, as I was talking about that. It's trying to learn like the goodness of each state, where goodness corresponded to probability of winning based on like all the millions of games I've seen before. Turns out that's a far better metric than approximating it by how many points I'm up by. And this is why you get behaviors that aren't intuitive to humans, because we've been fundamentally playing the game badly all this time, because we're really bad at like running infinite simulations in our heads to figure out like how the world's going to pan out. And I think that's just a really interesting kind of microcosm on what happens when you're incentivizing different kinds of behaviors.
Yeah. So we're coming to the end. I just want to ask one last thing about a conversation that's been that has exploded in the last week or two, which is that was prompted really by Mustafa Suleiman's comment or an article in which he said that there's a problem of AI psychosis, that people who think that large language models are conscious, and there's a lot of people who do, and I know this because we get emails from a lot of them. There's a very strong consensus among the scientific community that they are not conscious yet. And Mustafa Suleiman is very worried that people are, getting confused, and they're being misled by the providers of the models, and that he thinks it's extremely dangerous. Now, you spend your life getting cute little robots to do things, and I'm sure you also spend a lot of time working with using large language models as well. So you're probably, as vulnerable as anybody could be to this over attribution. Do you think it's very dangerous? Do you take any steps to avoid yourself giving them names or anything like that?
I mean, it's funny, we do tend to name our robots, and this has like always been a thing, even when their behaviors are terrible. It's weird how happily humans anthropomorphize things.
Yeah.
It's
I
like
have a name for my car and things like that.
Right, exactly. And we, I always point out to people, like, humanity went through a phase of pet rocks. Like,
Yeah.
that's fairly different to another human. But we do this anyway. And so I think, you could think about this in different ways. To me, there are a couple risks. Now, I think maybe the on the surface anthropomorphizing things, lots of people make a big fuss about it. Firstly, I think it's useful for explaining many concepts. As a form of like metaphor or analogy. It's also useful because like, to some extent, we've got very good kind of social wiring in our brains. And, if we can employ that in certain situations, that's like toolboxes we can port over. And I suspect that's why we do these things, because if you can say situation A looks like situation B, I get to use the same toolbox in that setting. Kind of what I've been talking about here in terms of transfer. I think that's very much like why we do it, because it's a very useful skill. Now, why might it be a challenge to think about this? I mean, so I worry about the setting where most people just assume all machines are conscious, and this like stops being an interesting question. Now, to me, this is like the most interesting and most important question. Is like, is about machine consciousness, and for a couple of reasons. One, I think if we do build machines that are conscious and we're not aware of it, and we're causing tremendous harm to them, then like that's incredibly immoral. That's as immoral as, and in fact, possibly, we don't know how we're measuring this, but like you could imagine, because why not, that we have machines that are capable of suffering far worse than humans can suffer, or and in that case, if we go and accidentally build these things, we don't have a good way of evaluating it, and we're just like causing like, complete devastation levels of suffering, that feels pretty monstrous. On the flip side, if machines are not conscious, but we think we think they are, I think there's risks of like that kind of Westworld scenario that, you find yourself in a situation where people say, oh, you can do anything to machines, they're not conscious. And like, maybe we can even prove that they aren't conscious. But they're similar enough to humans that it actually has a bearing on how we treat other humans. So if you're in the Westworld situation where you can just run around and shoot other things that look exactly like people and do so, and people and you get told this is absolutely fine, like it's a machine, it can't suffer, but and even if that's true, it can't suffer, but now what is that doing to your own mental circuitry for that something that to you is indistinguishable from a human, in appearance or behavior or whatever it is, like that's got to have some sort of impact on your own like morals and ethics and even what you're capable of doing. And I think there's risks there of like what that could mean for like just society in general, our interpersonal relationships. So I do think that there's a lot riding on us figuring out how to quantify this, how to identify when it's happening, and ultimately building towards it. I'm going off topic a little bit here, but I have another kind of feeling that when what's super interesting about thinking about machine intelligence is, machine consciousness is, we've got all these questions around like, we don't know why we have consciousness and that kind of thing. But, in kind of pre-modern AI days, we had, okay, humans are conscious and we can say certain things about the other living creatures and the extent to which they're conscious, or we believe them to be conscious and so on. But, we always had this thing where we talk about intelligence, so we can say like, intelligence, to be the most intelligent, you've got to be able to write poetry. To be able to express emotions, you've got to be able to, basically be humans. Now we have two data points. Like we have two different kinds of systems that we know can write poetry, right? We got our large language models and humans. And to me, this is super interesting because if you've only got one instance of something, it's very hard to see what's general about it and what's specific about it. The second you have more than one, and I mean, we even use this principle in our own work. The second you have more than one, you can kind of start seeing like, where are the commonalities? So the kind of thought experiment I go through here is like, okay, we now have two machines or two devices, two entities that can write poetry. We've got humans and large language models. There's a very crude approximation by which, our neural networks work like brains. So there's some vague mapping between them, but like they're fundamentally different mechanisms. Again, this is interesting because they're each going to have different pros and cons and different strengths and weaknesses. Now, one hypothesis might be that there's multiple ways to get to the same level of intelligence. You know, the intelligence that can write poetry and that sort of thing. But potentially, the reason we have whatever it is that consciousness is that if you're going to get to that point with like the kinds of physical constraints of our head, the kind of energy constraints of like just the food we eat, you know, your 20 watts or so that's powering your brain, you need something else that's maybe handling this like this radical attention mechanisms, these techniques for like controlling what you're focusing on, that kind of thing. Maybe you don't, maybe that's not the only path to get to human-like intelligence. Maybe as an alternate, if you could give infinite data to a thing and infinite compute and all the electricity it needs, maybe it can get there via another means that doesn't require, like, doesn't have the same bottlenecks, and so maybe doesn't require a consciousness to get there. Like, I think these are interesting questions that we can think about because we have multiple data points, and that allows us to run different kinds of experiments and test different hypotheses. At least that's kind of my a working hypothesis of mine at the moment. But again, I think like this era of thinking about what are the capabilities of these technologies, how can we push them, helps us get to be able to think about this kind of question.
Yeah, no, I absolutely agree. I think one of the great advantages if we do create conscious machines, we'll be learning about our own consciousness and learning about consciousness in general. It does seem to me extraordinary blinkered to think that the only way to create consciousness is the way it happened to arise in us. That seems quite unlikely.
Exactly.
Anyway, Benji, this has been really great. Thank you very much indeed for taking the time. Thank you for everybody for joining us. As I said on the chat, a recording or video of this will be made available on the Meetup website within a week or two, and there are some videos I think of some of the previous meetups on there as well. But so Benji, once again, thank you very much. Congratulations on your elevation to the top 100 up there in pole position, and we'll see you all again next time.
Yeah, thanks so much, and thanks everybody for listening in and watching. And it was great chatting, Kevin.